Okay, we're going to finish up chapter 18. I'm at the bottom of page 110. What we just talked about was ether cleavage and epoxide ring opening. We're going to continue with the epoxide ring opening, only now we're going to change it to basic conditions. In other words, these are cases where we have bases, and the bases by and large will be Lewis bases, so on and so forth. And this is a lot easier. It's a lot easier. Why? Here's why. Because the nucleophile will attack the least hindered position. Will that happen all the time? Yes, it will. So keep that in mind. So this is going to turn out to be very simple. You don't have to worry too much about primary, secondary, tertiary, any of that, SM1, SM2. It's always going to be the nucleophile attacking the least hindered position. But I still encourage you to do what we did before, and that is address the order of the carbons, okay, that are part of the epoxide ring system. Okay? So here we have a tertiary carbon, and over here we have a primary carbon. So again, that's going to give us a diol. So how did it happen? Okay. Folks, as you know, if you place sodium hydroxide in water, what's it going to do? It's going to dissociate into its respective ions. So in this case, we have hydroxide anion. And of course, we have sodium cations. Well, where is it going to attack? There or there? It's going to attack the least hindered position. Okay. So this hydroxide, that hydroxide becomes hydroxyl. There it is, right? It attacked the least hindered position. It's a real simple process to understand. Now, just looking at that, you say, well, how do you know that? How do I know that that OH wasn't this OH or vice versa? There's a way to study that, and that's what I have on page 111. Let's take a look at that. What we want to do is we want to follow an isotopically labeled oxygen around. It says predict the structure of the 1,2 diol from the following reaction. Okay? Now, here we have oxygen that's been labeled. This is O18. Okay? And this oxygen has 10 neutrons. It's a heavy oxygen. And there is such a thing as oxygen NMR that will allow you to see that. Okay. Now what's the order of that carbon? That's a tertiary carbon. And what's the order of that carbon? That is a primary carbon of the epoxide. Where is it going to open? It's going to open here, right? It opens here. In other words, that bond's going to break. Because the nucleophile, in this case hydroxide, is going to attack here. Now, the way that would work, if you want to see this in a little greater detail, is that we're going to go ahead and show the alkoxide intermediate. Okay, because you might wonder, how do we get that proton from that one carbon? Let me show you by providing the intermediate. Okay, so here we opened up. Okay, there's that oxygen. Putting on the lone pairs. There's the negative charge. Here's the 18. Here's the hydroxide that came in, okay, to the least hindered spot. Okay. And so this is an intermediate, right? We're not quite done. So you say to yourself, well, how do we get a proton? How do we get a proton on that oxygen? Well, there's water around, right? Kind of running out of space, but I have to do it up here at the top. Water we call is a very weak acid, but it's suitably strong for an alkoxide. So that's what happens, folks. You simply pick up a proton from water and to get more hydroxide back. Nonetheless, this is stoichiometric, okay? It's stoichiometric quantity of sodium hydroxide in order to carry out this reaction. So the final structure would look like this. Now the reason I'm drawing that C there, the C, you don't have to do that, just so you can see that carbon a little more plainly. But you can just go ahead and connect that with the angles. So here's a CH2, and condense that down. Here's an OH, and there's our OH there. And I'll remind myself that it's labeled, and there's your product diol. Okay, remember what a diol is. You have OHs on adjacent carbons. So there's a OH on that carbon, there's an OH on that carbon. Now back in chapter 17, we talked about Grignard reagents. Grignard reagents are really strong bases. Okay, they are among the strongest bases you'll find. So here's your Grignard reagent. And so I think the best way to discuss this, how it happens, okay, is to go ahead and just separate it out into its components. This ethyl magnesium bromide. Right, so here's a F5 anion. In other words, a Grignard reagent is the source of F5 anions. And I didn't label the carbons, but you know what? What's going to happen here? It's going to attack, right, that carbon, because that's where they always attack. There's no protonation involved here, guys. So that epoxide will open up simply by virtue of the fact that you have such a strong nucleophile. Okay. Now let's draw the intermediate after the we do the Grignard. Okay. What does it look like? The intermediate we have after the Grignard is the same as with any Grignard. You have an alkoxide intermediate. Alkoxide intermediates are characterized by sp3 oxygens bearing negative charges. So here's our methylene. And what did we attach to that methylene? We attached an ethyl group that came in the form of a Grignard reagent. Alright. Now, there's our lone pairs. Now what's ammonium chloride for? It's there to quench, right? It's a proton source. So just put that as H+. That came from the ammonium chloride. And there you go. There's your product alcohol. So you get the higher ordered alcohol. In this case, we get a tertiary alcohol. So if you're asked, well, where all the different things come from, folks, these two carbons came from what? Came from the Grignard reagent. It's these carbons there that added to that epoxide ring system. So the Grignard reaction, okay, is not just with carbonyl species, it's also with epoxides. Bottom of page 111, we have sample problem 18.16, and this is called styrene oxide. Okay, what's our Grignard reagent? Methyl magnesium bromide. What's going to happen here? Methine anion is going to attack, right? It's going to attack right there. Pop that ring open and form a carbon-carbon bond though between the methylene and the methine. Then we're going to protonate that alkoxide intermediate, and we end up with a brand new alcohol. Okay, so let's go ahead and sketch that out. So here's our phenylene. Right. And here's that methylene. That methylene has a methide attached to it. I'm switching colors so you can see where everything's coming from. And of course, this is the OH. And there was a pre-existing hydrogen. Alright, so a little bookkeeping. Where did that methide come from? It came from the Grignard. Where did this proton come from? It came from the ammonium chloride. So these problems are very simple to understand. Bases always attack the least injured carbon. Now another kind of base we have is an amine, right? So let's go to page 112. I've actually done reactions like these back when I was an undergraduate. This is a reaction with a primary amine. So these can undergo reaction with ammonia, primary amines, secondary amines, but not tertiary amines. Okay, that's different. And these things on the right are called amino alcohols. So let's get a feel for what's happening. Now, primary amines are always characterized by NH2s. So you see an NH2 bonded to a carbon. But the real reason they're called primary is because the carbon that bears the nitrogen has only one carbon attached to it. It works the same way as alcohols. Alright, so this will act as a nucleophile towards that methylene. We're going to open up the ring. And then let's catch the intermediate just so we can see what other process may be taking place. Now, to make this a little simpler, I'm going to abbreviate the phenyl ring with the letters pH. Okay, keep things a little bit simpler for us. Alright, so there's that oxygen now. Here's that methylene. Okay. Let me go ahead and put the lone pairs and the negative charge on the oxygen. Let me sketch in this remaining portion. Here's a nitrogen that attacked as a nucleophile, and it has 2 protons because it was an NH2, and it also has 3 carbons. And there's the plus charge. Okay, so that's what happens when the nucleophile attacks there. Okay, now the last step is we need to get that proton from here to there. That can happen intermolecularly or intramolecularly. If we show this intramolecularly, it makes sense because look, we go from 1, 2, 3, 4, 5. In other words, they're not that far away, folks. Okay, if it would curl up a little bit, so the lone pair here can grab onto that proton, and that pair of electrons returns as a lone pair. So this would be an intramolecular proton transfer. It is, but it can happen intermolecularly as well. Either way, we don't really know. It just depends on how concentrated the solution is. Now, secondary amines work the same way. Okay, this is the secondary amine. Why? Because it has 1, 2 carbons attached to the nitrogen. Secondary amines are characterized by NH. And what's going to happen? Well, you already know. The lone pair will go here, attack, pop it open. It's the same type of mechanism above. Now, what's your job? One of your jobs, and this would be the most important one, would be to predict what the product is. Okay? Okay. And that would be true with both cases. Now, since this is an amino group and this is an alcohol, both of these things are called amino alcohols. Okay. This is an amino alcohol, and that's an amino alcohol. So if anybody ever asks you, how do you make an amino alcohol? I said, well, I could react an amine with epoxide. As you know, organic chemists are given the task of how to make compounds. It's very important. And so what we want to do on the bottom of page 112 is figure out what epoxide and what amine we would need in order to produce this amino alcohol. Okay? The way that you can do that is to kind of work in reverse, right? You have to work in reverse. What I mean by that was, where's your new bond? Okay? Could you find the new bond over here? Where is it? I hope you recognize it's that one, right? The one I just colored in yellow. That's your new bond. Let me indicate that. We know the new bond was established when an amine, okay, attacked the carbon. So there's the amine, that must be the new bond. And when it made that new bond, didn't it open up an epoxide? So wouldn't you say that this oxygen was originally bonded to that carbon? That would make a 3-membered ring. With that in mind, we can figure out our amine pretty fast. Okay? The amine component is simply a phenyl ring with NH2. Okay? And by the way, this is known as aniline. Okay, if you ever heard of aniline dyes, they have these particular functional motif in them. Then our epoxide is simply reconstructing this by joining that oxygen to that carbon. So when you draw epoxides, you've already gotten practice of it, but go ahead and draw your three-membered ring first, like this, your skeleton, and then attach the things that it should have. So here we have a methylene. We just do that as CH2. And over here, though, we have two methyls, so I'm going to show those independently. So this would be the answer to the epoxide, okay, and the amine necessary to produce this amino alcohol. Okay. Now we're going to start shifting gears completely, finish up the chapter. And I'm looking at page 113, okay? Folks, we have something known as crown ethers, and they're really, really fascinating compounds. This was the very first crown ether ever discovered. It was by Charles Peterson. He worked for DuPont. He actually won the Nobel Prize in chemistry, but interestingly, he did not have a PhD. He had a master's in chemistry, but he was wonderfully intelligent. So what they're used for is to sequester cations, okay? So what does that mean? What it means is this. Folks, suppose I had potassium cation, okay, K+. Turns out that fits beautifully inside here, okay? Sodium does as well. And it's just about impossible to get it out of there, right? So this would be a potassium complex whereby it's embedded in between these oxygens. Now I'm going to explain what these numbers mean. Okay, so you'll have some idea of why they're called what they are. But I can't emphasize the importance of how this just opened a new paradigm in chemistry. It's just amazing what this led to, the discovery of all kinds of new compounds. And it's also linked to what we call nanotechnology. It's really important. But here's how this works. If you made a model of these, they look like crowns, okay? Like a crown. The 18, right? That's just the total number of atoms in the ring. Go all the way around, there's 18 atoms in that ring. In other words, you can see that there's 6 oxygens, right? You can see that there's 12 carbons. So 12 plus 6 is 18. Shapes like a crown. 6 refers to the number of oxygens. And finally have the word ether. So this is 18 crown 6 ether. Over here the same, smaller. 15 crown 5 ether. There's 15 atoms in the ring, 5 oxygens, and it's an ether. So this is 15 crown 5. So here's how you name these things. X, crown, Y, ether. X is the total number of ring atoms. That is the oxygens plus carbons. And Y is simply the number of oxygens. So whatever number that is, it's the total number of carbons and oxygens, and whatever number that is, the total number of oxygens. Let's sketch a very simple crown ether. 12 crown 4 ether. 12 crown 4 ether. Okay. I've drawn a lot of these, and the best way to do them is to draw the oxygens first. So I'm going to space them out like that. There's my 4 oxygens. And all that you have to do after that is bridge them with ethylene groups. So there's an ethylene group. There's an ethylene group. There's an ethylene group. And finally, there's an ethylene group. So this would be an example of 12 crown 4 ether. Okay? It's really, really small crown ether. Alright. Fascinating stuff. Let's move to the last part of the chapter. It deals with thiols and sulfides. Okay? Something we addressed at the very beginning. But let me just make some general remarks. Folks, thiols, anyway, you see the word thi, T-H-I, you should think of sulfur. Right? So the chemistry is pretty similar to that of oxygen. So thiol is a sulfur analog of alcohol. We have an SH in place of an OH. And thiols are oftentimes called mercaptans. Okay, and the reason they're called that is because they can use them to capture mercury. Mercury spills. You pour sulfur over mercury and it will capture it and make a complex. So they're called mercaptans. And the SH is weakly acidic. Okay, they have a pK of about 10. It varies. So they're actually more acidic than alcohols. However, unlike alcohols, there's no real hydrogen bonding. Okay. For hydrogen bonding, you need fluorine, oxygen, and nitrogen, but the electronegativity, sulfur is not that different. It's about 2.5, so therefore the sulfur-hydrogen bond is not very polar. Now, thiols are very sneaky. Skunks have thiols in them for their defense mechanism, and most things that smell really bad, even onions have some thiols, garlic have thiol. Okay, doesn't really smell that bad, but depending on the concentration. Now let's look at the nomenclature of thiols. Okay, so I'm going to page 114. Show you some examples. Here's some examples of thiols. This would be ethylene thiol. Okay, for obvious reasons. This is cyclohexane thiol. Okay. So if you have an alkyl group, you just name the alkyl group followed by the word thiol. No more complicated than that. However, if you have an SH group that's part of an aromatic ring, we call it mercapto. Right, see the SH is part of the aromatic ring. So you may remember what toluene was. Toluene is methylbenzene. So this would be orthomercaptotoluene. Right? Pretty straightforward. Now that brings us to the parent compound for that, which is called thiophenol. What would thiophenol look like? Well, you may remember what phenol was. What was phenol? Phenol has an OH group, right? So here, we have an SH group. So this would be thiophenol. And then finally, what would metamercaptobenzoic acid look like? The benzoic acid was one of those that you needed to commit to memory. So let me draw that first. Now you can write this condensed with CO2H, or you can do it that way. So there's benzoic acid. So you need to locate the meta position, and that would be here, okay, or there. And what do we have attached to it? A mercapto group. So this would be an example of metamercaptobenzoic acid. Alright. Now the reason I left the first one blank is it seems a little bit contradictory to something that we had in Planck's gas. Okay. Somebody decided that if you have an SH group as part of a cycloalkene, that the carbon 1 would be where the thiol group is. So let's go ahead and sketch that. So we know we have a 5-membered ring, right? Cyclopentene. So to make it a cyclopentene, I need a double bond in there somewhere. And where would I attach my SH group? Okay. Well, interestingly, this is kind of bizarre, but the SH group would go here. So this seems to be very contradictory to things that we learned back when we were discussing cycloalkenes. Right? So folks, I'm not going to have this on your exam, right? Because it's just different. This is not on exam 3. So don't worry about it. If you worry about it, don't be. Alright, but these all are game. Alright, I have you name those or something to that extent. Okay, let's move into the last part of this. let's talk about how you would make a thiol. In other words, how do you synthesize a thiol? It seems pretty simple, but it turns out there's some underlying complexities. One way to do an SN2 reaction with this hydrosulfide anion, that's this, okay? And folks, that is a really strong nucleophile. It's one of the strongest nucleophiles out there. Okay? It really is, very strong. So that's how this would work. Okay? You simply have SN2 displacing a leading group, okay, off of a primary halide. Now that seems pretty good, right? Whoa, we got our FH group there now. But here's the problem. This is a good nucleophile as well. Okay, this is a good nucleophile. So what would it do? It would go back and react with the primary bromide as well, giving you a sulfide. So if you use this process, the yields are low because the thiol is a nucleophile as well. Now, one way to get around that is just to use a huge excess of this, okay, so that statistically you minimize this behaving as a nucleophile. And but there's another way to do it. The other way of doing it, though, involves two steps, but you get much better yields. And the better approach is that of using thiourea. What is thiourea? Thiourea is a sulfur counterpart of urea. For those of you who had lab, okay, you may remember that urea, which is a mammalian byproduct, okay, has this structure. Okay, that's urea. This is urea. But replace that oxygen with sulfur, you suddenly have thiourea. Okay? Thiourea will react with primary halides and also reacts with secondary, but not tertiary, and then ultimately end up with the actual product you were looking for. In this case, what do we have? 1, 2, 3, 4, 5, 6, 7, 8. Okay. We have octane thiol. Did I do that right? 1, 2, 3, 4, 5, 6, 7. Yeah, octane thiol. And interestingly, what do you get for byproduct? Urea. Didn't have to draw it twice, but I did. Now the mechanism is pretty involved. If you look at page 552 of McMurray, you'll see a partial mechanism there. But don't be overly concerned about the mechanism, but this is a much better approach. Drawback, it's two steps, okay? The first step is treatment with thiourea, followed by the hydrolysis of an intermediate using base. Let's go to page 115. All right, and on page 115 there's some information, just for your information only. We talked about how to synthesize disulfides, so on and so forth, okay? And these are fascinating things, particularly if you study biochemistry, right? But this is for your information only. Okay? I really like this stuff, but we're not going to talk about it in great detail, but there's a way to make a disulfide, okay? There's a way to reduce a disulfide using these sets of conditions. So let's talk ever so briefly about sulfides, particularly their nomenclature. So again, let's just remember what's going on. Not that complicated. Sulfides are the sulfur analogs of ethers. In other words, we're going to have sulfur in place of oxygen. The nomenclature is pretty similar to ethers. Okay, you're going to replace the word ether with sulfide, and or you might have to replace it with the alkyl thiol group. So I've got some examples here. These examples will help you understand by symmetry. So at the outset of the chapter, you called this diethyl ether, right? Okay? So what would this be? We're replacing the oxygen with the sulfur. This is simply diethyl sulfide. Very simple. Very easy to understand how you would name that diethyl sulfide. Look at the next example, which would be methyl phenyl ether. Okay, that's a systematic name. Well, this is methylphenyl what? Methylphenyl sulfide. So all that we have to do is replace the word ether with sulfide. So here again we have another simple example. Look at this one. Okay, this would be 3-methoxycyclohexene, and the reason it's 3-methoxy is because we would number it like that. We have to pass through the double bond, and we need to have that 3 in the name to indicate the name. All right. Now, what is this group here? Okay, this group here has its own subname. Okay, it's methylthiol. Okay, methylthiol, not methylthiol, but methylthiol. But we're using the the same numbering sequence. We go 1, 2, 3. And so that's why this is called 3-methylthiocyclohexene. And then I give you a little explanation here. Well, McMurray, the guy who wrote our book, says he places alkyl thiol group in parentheses, so on and so forth. So there's a little bit of nomenclature, very easy to understand if you understood the nomenclature of ordinary ethers. Alright, here's our last part. How do you make sulfides? We use a very similar reaction as in the Williamson case. Okay? So let me just show you one example of that. Suppose you had thiophenol. Okay, what do we know about that proton? Now the acidity of about, I'm guessing about a little less than 10. Treat it with a strong base, and then you get this intermediate. Okay? And this is a really good nucleophile. So this is step 1. No different than Williamson. Okay? Same thing that you were talking about earlier. Now you don't isolate that, but instead, in step 2, what do? Step 2, you add an electrophile. And so in this case you have a very good electrophile, methylbromine, and you end up displacing a bromide. So here we made methylphenyl sulfide, the same compound we had right there. Right. That's how you can make it using Williamson style chemistry. Alright. Let's go to page 116. It says complete the following synthesis by providing the major organic product. Okay? So there we have a series of reactions, and you may be under the impression that you have to figure out, everything that we get along the way, but you really don't. You just have to understand how these reactions work in tandem. Let's begin by addressing this bromide, okay? This is the primary bromide, right? This is called a primary halide. What did we say that thiourea followed by basic hydrolysis was for? Wasn't that for converting halogen into sulfide? Right? I'm sorry, a thiol. We're going to replace that Br with an SH. Now to make this a little simpler, let me just draw zigzag structures, okay? So we're going to do step 1, we're going to do step 2, and let me draw a zigzag structure here. We have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. And where you formerly had a Br, what are you going to have now? You're going to have an SH. Okay? So you could actually isolate this compound, purify it, characterize it, whatever you needed to do. Now what did we say the last step was for? What does sodium hydride do? It removes that proton. What does ethyl iodide do? It serves as an electrophile. So we're just combining these reactions that we just saw in the previous pages. So now we're going to do steps 3 and 4. Okay? So here's that sulfur. But what would you have attached to that sulfur now? Ethyl group. So there's your final product, which is your sulfide. So this is how you can go from a primary halide, and it could be secondary as well, to a sulfide. to the sulfide. Alright. Now, let's take a look at these synthesis problems I have on the bottom half of page 116. Here, you may notice that we have two arrows. And what that means is you have to do multiple steps, and that's what all this space is for. Okay? So, the goal here is to transform this ester into a thiol. So somehow, some shape, some form or another, we have to transform that into this. So we're going to have to use the chemistry that we had learned earlier. Now, one of the things that I taught you earlier was that you can reduce esters to alcohols. Okay? So why would we need an alcohol? Because you can easily convert that into a thiol. Right? Okay. So you remember how to reduce that? Now esters they're kind of hard to reduce, so you need a strong reducing agent. So in this case we're going to use lithium aluminum hydride. And usually that's conducted in a solvent like tetrahydrofuran or something of that nature. But I'm going to leave the solvent off because it just clutters things. But then you have to work it up using water, or you could use hydroniumide or something to that effect. But by virtue of you doing that, you're going to reduce this ester to its corresponding alcohol. Right? So to make that a little simpler, I'm going to point that OH up like this. Okay? Just so you can see it was that oxygen that became that oxygen. So we have a primary alcohol intermediate now. Alright. Now, how would you go from a primary alcohol intermediate to a thiol? Something we learned earlier. Well, let's turn this into a bromide like we have there. Now, there's more than one way to do that, but recall that the best approach is to use PBr3. Okay. Now I'm showing the solvent. If you don't show that solvent, no big deal. But this is going to result in converting that into what? A Br. Let me just draw it out like this. So suddenly we have a primary bromide. And now we have a sequence of reactions much like that one. Okay. What did we do? How do we go from a bromide to a thiol? The first thing you have to do is treat it with what? Thiourea. Now you can just write the word thiourea, or you can draw the structure. But thiourea, okay, is going to make an intermediate whereby that bromine gets replaced with the sulfur. Then you have to hydrolyze off the remaining part of that intermediate using sodium hydroxide and base. Sodium hydroxide and water. And that would give you that. So this is a good one to look over if you are interested in synthesis. Okay? Now, let's look at the very bottom on page 116. Here we have to think back to chapter 14. Okay? And what I mean by that is that we have this conjugated system where we want to migrate that bond. Remember how to do that? Jogging your memory here. Folks, if we add HBr to this, the low temperature for a short reaction time, we get a Markovnic competition. And that's not going to help us. But if we want to get a thermodynamic product, we number these carbons 1, 2, 3, and 4. If we want a thermodynamic product, we can add HBr, and that pi bond is going to migrate and get a 1,4 addition. So I'm going to write HBr. Okay. Let me write in high temperature, high T. Okay. And also it would be for long reaction times, but this suffices, HBr at high temperature. Now what that means is sure, you're going to get the bromine attached to carbon 1, okay? But because it was high temperature, the pi bond is going to migrate between carbons 2 and 3. Okay? So now we have this particular bromine. And then this becomes a problem just like the one we had above. The fact is it's almost identical, isn't it? It is identical. What would we do? Remind ourselves what we do. Step 1, we have to take thiourea. And then we have to hydrolyze off that using sodium hydroxide and water. So these were 2 reaction sequences, okay, that gave you the same product, but we started with different materials. And just in case you were wondering, this compound, trans-2-butene-1-thiol, that's just one of the components of skunk spray. And you can imagine, that smells pretty bad. Okay, last page. Page 117. Folks, here I describe the oxidation of sulfides to sulfoxides and sulfones. It's really very easy to understand. Okay? And so I just want to give you a feel for that. But really it's kind of a name that will help you understand this. But you may have to think back to what you had in Organic 1 before you can really do this. So when I say RSR to RSOR, that's a sulfide and this is a sulfoxide. And that's really easy to do. To take a sulfide though, to a sulfoxide, again it's easy to do, but to take a sulfoxide and go to a sulfone, that's a little harder to do, so you need a stronger oxidant. So this is what goes on. And this is the kind of thing actually happens in nature. That's why over time, things that smell really bad, they don't smell so bad because they get oxidized very heavily simply by exposure to oxygen in the atmosphere. But here, focus on what I'm saying. This is methylphenyl sulfide, right? Notice the sulfur in the middle, it says sulfide. We're going to take aqueous hydrogen peroxide. And this step here is very easy. And this is so easy to do. Okay, just mix in a little peroxide, stir it for an extended period, and you got yourself a sulfoxide. Notice now we have a doubly bonded oxygen. So this went from really smelly to not so smelly. And then finally, if you want to oxidize it further, you need a strong oxidant. In this case, peroxyacetic acid. This is harder to do. Harder to do in that it's harder to get a second oxygen on there. But this is how you end up with a sulfone. Okay, sulfones are characterized by having 2 oxygens bonded to a hypervalent sulfur. And there's one more section in the book. Okay, go ahead and omit that. Alright, so we'll stop right there. And we'll pick up chapter 19 a little bit later. Talk to you later, guys.